Welcome to the smallest projective space on the tetrahedron. We're going to have a look at all kinds of interesting geometrical objects associated with this space. The space has 15 points represented by the black spheres, 35 lines, and 15 planes. Let's first have a look at the points. There are essentially 4 different kinds of points. There's the center of the tetrahedron. There are the centers of the 6 edges. There are the centers of the 4 faces. And there are the vertices of the tetrahedron. So this gives a total of 1 plus 6 plus 4 plus 4 equals 15 points. There are 6 different kinds of lines in this model. Here's the first kind. These are the edges of the tetrahedron. There are 6 edges of the tetrahedron. Then there are the 12 medians of the faces. The 4 medians of the tetrahedron. The 3 diagonals of the tetrahedron, the circles inscribed in the 4 faces of the tetrahedron, and 6 ellipses inscribed in the tetrahedron. Every single one of these ellipses touches the tetrahedron in one of the edges and 2 of its faces. This gives a total of 6 plus 12 plus 4 plus 3 plus 4 plus 6 equals 35 lines. There's also a beautiful flat model of the space that we're going to look at now. It has essentially 3 different kinds of points. Here's the first kind, the second kind, and the third kind. So again we have 15 points. There are essentially 7 different lines. Here's the first kind of line, second kind of line, third kind of line. You arrive at all the other lines by rotating this model 72 degrees at a time 5 times. This gives a total of 7 times 5 equals 35 lines. The pencil of lines through a point is just a set of all lines through a point. There are 4 different kinds of points in the space, so there are 4 different kinds of pencils in the space. Here's this pencil of lines through the center of the tetrahedron. And here is the pencil of lines through one of the vertices. You notice that every point, not the vertex, is contained in exactly one of the lines in the pencil. So this will be true for all the pencils in the space. This implies that any 2 points in the space are contained in exactly one line. How do you see this? We'll take the first point, look at the pencil of lines through this point, then the second point is contained in exactly one such line. In the flat model, there are 3 different kinds of points, represented by the 3 points on the yellow line here. So there are 3 different kinds of pencils. Pencil 1, pencil 2, and pencil 3. There's also 4 essentially different kinds of planes. Here's the first one. Every plane contains 7 points and 7 lines. 2 points are contained in exactly one line, and 2 lines intersect in exactly one point. Here's a second kind of plane. It should look very familiar. It is a restriction of the projective space to one of the sides of the tetrahedron. We show the tetrahedron only for easy reference. In the third kind of plane, you see nicely how one of those ellipses is embedded inside the tetrahedron, touching one of the edges and 2 of the faces. The fourth kind of plane lives on a cone. Now 2 planes in the space intersect in exactly one line, which makes the space into a pretty perfect universe. What we're going to do now is go back and forth between 2 planes, actually flick back and forth, and you see one line seems to stay fixed. This is the line the 2 planes intersect in. The other thing this flicking back and forth shows is some kind of isomorphism between the 2 planes. Now here, one of the edges of the tetrahedron stays fixed, and again you see some kind of isomorphism happening. And even here, you see some kind of isomorphism happening. A spread is a set of 5 lines such that every point in the space is contained in exactly one of the 5 lines. Here's the first kind of spread. There's essentially 5 different kinds of spread in a space. Here's number 2. And here's number 3. Number 4 and number 5 have a very special property. So here's number 4. Now look at any kind of circle, any kind of median of one of the faces, or median of the tetrahedron. Then exactly one of the images of this spread under rotations will contain this line. Similarly, in the 5th spread, give yourself any ellipse, any diagonal, or any of the edges of the tetrahedron, then exactly one of the images of this spread under rotations will contain this line. This means that given any line in the space, one of the images under rotations of the last two spreads will contain this line. Now, the images we just mentioned, there are 7 of them. These 7 spreads form a so-called packing. We'll come back to that. Now, in the flat model, you have essentially 12 different kinds of spreads. There's the first one, having an order 5 symmetry. The second one having an order 2 symmetry. In fact, all the other spreads have order 2 symmetries. So you have one with an order 5 symmetry, plus 11 with an order 2 symmetry. Every single one of those 11 stands for 5 spreads. This gives a total of 1 plus 11 times 5 equals 56 spreads. A packing is a set of 7 spreads such that every line in the space is contained in exactly one of the 7 spreads. We've already come across one packing. Remember this spread here? And that one? The images of these 2 spreads under rotations of the tetrahedron form a packing. Let's have a look at the flat example. So 7 spreads, and we want to convince ourselves that given a line in the space, this line is contained in exactly one of the spreads. So there are 7 different lines in the space, and we're going to cycle through them and convince ourselves of this fact. So here are the yellow lines. The blue lines, and so on.